In the last video, we covered the fact that light is a wave, that waves require a medium in which to propagate, and that the dismissal of some form of ether as that medium was a conclusion the evidence never actually supported. In the theory of wave physics, we call this medium the membrane, or M. In the book Wave Physics version 2.0, we also refer to it as the substrate. We can deduce some of its properties directly from things we already know. The first property is tension. Without tension, a wave would not oscillate because there would be no restorative force. Light waves occur, and they appear to be the same speed from any perspective, so we know that there is tension, and we know that that tension is, or at least appears to be, consistent. The fact that there is tension means that there is some resistance to oscillation that has to be initially overcome. Any energy below that level results in the membrane returning to equilibrium since the energy is not enough to affect it, meaning that the law of the conservation of energy is a macroscale law with a structural limit. We also know that there appears to be a maximum speed. That speed is the speed of light in what we call a vacuum, and it is set by the physical properties of the medium. Light travels at 299,792,458 meters per second. That number is set by definition, but it is a result of the tension of the membrane and by its ability to equalize the pressure differentials that naturally occur from the motion of anything through it. The next property is zero viscosity. Objects move through space without any drag from space itself. A planet in motion stays in motion. Light crosses billions of light years and arrives at the same speed we measure light in a vacuum. Whatever the medium is, it offers no resistance to lateral motion. Its viscosity is exactly zero. Then we have the membrane's elasticity. When a wave passes through the membrane returns to flat. Radiation does not accumulate. It passes through and leaves the membrane in its original state. This happens every minimum unit of time. The membrane is not permanently altered by radiation. Another characteristic of the membrane is the capacity for persistent deformation. Not everything returns to flat. Some deformations are stable. They don't radiate away. They hold their shape against the restoring tension of the membrane. These persistent deformations are what we call matter. We will examine exactly what form they take in a later video. The final known property at this stage is that it appears to have no thickness. It may be that instruments more powerful than we have now will reveal that it does, but until that time we are treating it as a two-dimensional phenomenon capable of deforming and of extruding into the third spatial dimension. These properties tell us what kind of medium the membrane must be. To describe it precisely, we need units, and those units are not arbitrary. In 1899, Max Planck showed that three constants already measured by physics, the speed of light, the gravitational constant, and the reduced Planck constant, combine in only one way to produce a pure length, only one way to produce a pure time, and only one way to produce a pure energy. He called these natural units because they depend on nothing human, no artifact, no convention, no arbitrary choice of scale. Wave physics takes Planck's results and interprets those three unique combinations as the intrinsic resolution scales of the membrane itself. The first is the span, the membrane's minimum resolvable length, the smallest distance that constitutes a distinct location on the membrane. It is equal to the Planck length, approximately 1.616 times 10 to the negative 35 meters. The next unit is the tick, the membrane's minimum time interval, the smallest duration in which any state change can occur. Everything that happens in the universe happens in whole numbers of ticks. It is equal to the Planck time, approximately 5.391 times 10 to the negative 44 seconds. One span divided by one tick gives exactly the speed of light, which makes sense, since c, which is the speed of light, was one of the three constants used to derive them. But in wave physics, this is more than an algebraic consistency check. It means the speed of light is not a mysterious property of light itself, but a direct expression of the membrane's resolution geometry. The third unit is the Vulcan, the energy threshold at which the membrane's elastic property becomes plastic, allowing it to permanently deform. It is equal to the Planck energy, approximately 1.956 times 10 to the 9th joules. The fourth primitive is different. The shift is the membrane's minimum vertical displacement, the smallest out-of-plane movement that constitutes a real event. Just as the span sets the horizontal resolution of the substrate, the shift sets its vertical resolution. Unlike the first three primitives, the shift is not derivable from those three constants alone. Its value is estimated from the causal architecture of the membrane at approximately 1/30th of a span, roughly 4.85 times 10 to the negative 37 meters, about 3% of the Planck length, but its precise value remains open to further data. From these four primitives, without additional measured inputs, we can derive the quantum, the minimum energy a wave must carry to propagate across the membrane, approximately 3.97 times 10 to the negative 88 joules. That is an almost incomprehensibly small number compared to the Vulcan's 1.956 times 10 to the 9th joules. The dynamic range between the membrane's minimum response and its yield point covers nearly 100 orders of magnitude, which is like the difference between a whisper and an atomic bomb. A major goal in wave physics is to start with foundational units and build upward from there. We can't claim to have solved all of the riddles of the universe yet, but building up from the basics is a guiding principle we are following on our journey. The properties of matter, forces, and fields follow mechanically from these beginnings. Someone might ask, if the membrane is the substrate of the universe, then why don't we see it? That can be broken into two parts. Why don't we detect it with our senses? And why doesn't our instrumentation detect it? Both of those questions will be dealt with when we discuss radiation, but for our next video, we will examine what time actually is.